Okay, today we're doing the second practice problem for homework number 7. We'll begin as usual by restating the problem using a picture. So we have this long cylindrical rod and we're given some properties about it. Specifically, we know its diameter, which is 12 millimeters or 0.012 meters. We know the thermal conductivity K, which is 240 watts per meter Kelvin. We also know the density of the rod, which is 2,700 kilograms per meters cubed. And finally, the specific heat, which is 900 joules per kilogram Kelvin. We need to use joules there, so we match with watts. Okay, switching this around a little bit, now we have our cylinder, so looking at the end, the cross section, and going over this long cylindrical rod is some air. We call this cross flow. This air is moving at a speed of 8 meters per second, and it has a bulk fluid temperature of 30 degrees C, which is 303 Kelvin. Okay, in this problem, we are asked specifically to find two things. A, we are asked to find the surface temperature when we have generation. So there is a current passing through this rod, an electrical current, and because of resistive heating, we have heat generation inside of our rod. So we'll call that E-gen as a rate, and that is 1,000 watts per meter of the rod. So per meter length, we have 1,000 watts of generation. So that's part A. For part B, we are asked for an initial rod temperature of 30 degrees C, find the time for the rod to get within 10 degrees C of our steady state temperature, which will be the TS we're solving for in our steady state surface temperature model here in part A. Okay, so let's write down our approach for these two different problems. Okay, so for part A, we know that we're going to have convective heat transfer. And so we say Q convection is equal to our average heat transfer coefficient. Since we're looking at the heat transfer from our entire rod, we'll say H bar, times the surface area of that rod, multiplied by the temperature difference, Ts minus T infinity. Now, as a part of our approach, we realize we need H bar. So we're going to find H bar using the principles we've been learning lately. And then finally, we'll solve for Ts. For part B, we're going to, recognizing we have an initial temperature and we're asked about time, we recognize this as a transient problem. With any transient problem, we find the BO number, and then if possible, use lumped capacitance. Spoiler alert, we are going to use lumped capacitance. However, if the BO number was actually greater than 0.1, we would have to use a different method. Okay, before we move on, let's do our energy balance. So we have our cylinder, and we're going to draw our control volume around the entire cross-section of the cylinder. Inside of here, we have energy generation. So there's energy being generated, and we know that that must leave by convection, which we'll write as prime per unit depth. And we know there is no radiation because we are told to neglect radiation. Although in discussion at the end, we'll talk about how actually radiation would matter here. Okay, so let's go ahead and do this energy balance. We have the energy in minus the energy out plus energy generated equals the change in the stored energy. For part A, when we're finding the steady state surface temperature, we can remove this. Likewise, we have no energy entering, we just have energy being generated and energy leaving. So we can say energy gen is equal to what's leaving, and what's leaving is just Q convection. These could both be written on a per unit depth basis. where the dot, I've dropped the dot, but this would be the rate of energy generated. We already know that right here. The rate of energy being generated inside of our rod is 1,000 watts per meter. So we can just say that we already know the rate of convection. We know that the amount of energy generating in here must be leaving as convection. And so we know Q convection is 1,000 watts per meter. All right. So let's move into the analysis portion of our problem where we're going to follow what we've done here. So we know we need to find H bar. Okay, anytime we need to find H, that means we're in our convection chapters. And the first thing we do, anytime we want to find an H, a convection transfer coefficient, is we look up properties. We know this is air. I forgot to mention that. We have air. And anytime we look up properties, we need to know the film temperature. But we have a problem. We don't actually know what the surface temperature is here, correct? That's what we're looking for. So how do we find the film temperature? Well, in reality, what we would do is guess T surface, and then we would solve for T film and look up properties. And that's what we're going to do today. But we are going to use an educated guess because we already know the answer. At least the book knows the answer. And it advises us to assume a T film of 450 Kelvin. I bet you that will be close to the average of what we find to be T surface. So using this value in table A.4, we get a kinematic viscosity of 32.29 times 10 to the -6th meters squared per second. Okay, and we have a thermal conductivity of the fluid, that's important for the Nusselt number, of 0.0373 watts per meter Kelvin. And the last thing we always look up is the Prandtl number, which here is 0.686. Okay, we've got our properties, we have our energy balance. Let's go ahead and solve for H bar. But before we do that, we always need to know the Reynolds number. That is an important part of finding any convection transfer coefficient. So the Reynolds number would be U infinity times a characteristic length, or the diameter of our rod, divided by kinematic viscosity. So plugging in what we know to be U infinity, our diameter, our kinematic viscosity, we get 2,964, which for a cylinder, we use 2 times 10 to the 5th to designate laminar versus turbulent. That means we have laminar flow. Honestly, that's good, since those convections are a little nicer to play with. Okay, so here I'm actually going to change the solution. I'm going to do it differently than the book does. So the book uses equation 7.54, the Churchill-Coburn analogy, correlation, which is a fairly long and convoluted equation giving you the average Nusselt number as a function of the Reynolds number and the Prandtl number. That's nice because it applies for any Reynolds times Prandtl greater than 0.2, which of course we very much fulfill that criteria. So we would expect this correlation to be very accurate. However, there's another correlation, equation 7.52. This one is the Nusselt number average is equal to a constant times the Reynolds number raised to m times Prandtl to the 1/3. And this has a single stipulation, which is the Prandtl number must be greater than or about equal to 0.7, which you will notice we violate that by just a tiny bit. Because we're just on the cusp, I'm going to say this is easier, if anything, because it would take a significant portion of the board to write the other correlation. So we're going to use this one. You notice we have a C and an M, and you say, those are not numbers. How do I use this equation? Well, we use table 7.2. And there we look up for a given Reynolds number range. It gives us constants. So for a Reynolds number of 2964, using that table, we know that C is 0.683 and that M is 0.4 0.66. So we can plug those right into there, and then recalling that the average Nusselt number is just going to be equal to the average h bar. Ooh, that's what we're looking for, right? So that's great, we're getting close. Times our characteristic length divided by the thermal conductivity of our fluid, not the thermal conductivity of the metal. Do not get confused there. Okay, so now equating this equation right here to this equation right here, using these constants, we can then solve for h bar. Not going to write it all out, but you end up getting an h bar of 77.68 watts per meter squared Kelvin. Now, because I was curious, I also computed h bar using equation 7.54, which is probably more accurate for this specific situation, and got an h bar of 85.7 watts per meter squared Kelvin. So that's a difference of about 8, which is around 10%. I'm going to say that's all right, since our error is probably on the order of 20% for either of these, and move on. Okay, so we are ready to compute Q convection, which is h bar times the surface area. Remember, we're working prime per unit depth, so our surface area would just be the circumference of this circle, or pi times d, times Ts minus T infinity. Now, you remember that we actually know this value, right? We figured that out right here, that it's 1,000 watts per meter. We know d, we just figured out h bar, we're going to use this one, 77.68. We know T infinity, which was 30 degrees, so we can now solve for Ts using this equation. And when we do that, we get that the surface temperature is, let's see, 644 Kelvin. That is if you use this value for h bar. If you use this value for h bar, you get 612 Kelvin. Either answer would be correct, since there's error in these correlations right here that we're using. Okay, so that was part A. We will now move to doing part B, which you recall was to start with an initial temperature and find the time to get within 10 degrees C of Ts. Anytime we have a transient problem, what's the first thing you do? That's right, you find the BO number, which is our universal heat transfer constant. In this case, since we only have convection, we only use H, times the characteristic length for a cylinder, that is the radius divided by 2, divided by the thermal conductivity. But the thermal conductivity of what? Well, ask yourself, what are we modeling? We're modeling the heat transfer within this cylinder. So we're using the thermal conductivity of the cylinder, because that is what we're trying to find the temperature of. For the Nusselt number, since we were modeling heat transfer through a fluid, we use the thermal conductivity of the fluid. I bring this up because I'm sure some of you will miss this on the test. I'm trying to warn you in advance. Okay, so we know h bar. I'm going to use the value I found with the simpler correlation. We know the radius, we know k, so plugging those in, we get 0.001, which is definitely less than 0.1, so we are lumped. And because we are lumped, we can use lumped capacitance. However, you will be tempted to use equation 5.6, but we can't use equation 5.6, which you'll remember gave you T minus T infinity over Ti minus T infinity is equal to the exponent of minus A times T. I'm sorry, I don't recall the exact form. But this was derived assuming no generation, which is not our case. We do have generation inside of here. So now we must use more advanced forms, which are in the next section in the book. And going through, they give different simplifications you can do to the most general case. In this case, since we have no radiation, we can use equation 5.25, which looks something like this. T minus T infinity over Ti minus T infinity is equal to the exponent of minus a times t plus b over a over ti minus t infinity times 1 minus the exponent of minus a times t. Sorry, get a little overlap there. We're almost done. Okay, this seems pretty long, and how are we supposed to solve for t? Well, remember that we're asked to do this for ti of 30 degrees, but that's also what t infinity is. So ti minus t infinity is equal to 0, which looks scary since we're dividing by it, but let's multiply both sides, and it will cancel here, and this will then be multiplied by 0. We'll be left with t minus t infinity is equal to b over a times 1 minus the exponent of minus a t. Okay, a and b are functions of, a is a function of h and the surface area exposed to convection, or the circumference. B is a function of our generation. Both terms are divided by the density, the volume, and the specific heat. Taking those into account and solving for t, you'll eventually find 290 seconds is the correct answer. That is using an h of 85.7. If you use h of 77.68, you will get a different time there. Okay. Finally, as a matter of discussion, if you compute the radiative transfer from our surface, you will find that the radiative transfer is on the order of 200 watts per meter. I'll put in approximate, which, although less than 1,000, is still only a fifth of that. So we actually probably should not have neglected radiation in this problem. Okay, thank you for watching.